Okay. So, in this course so far we have sort of looked at first order logic as a language for representation and reasoning, and then we moved on to frames essentially, because we wanted to ease the task of computation. Today we will move to a new topic which is quite popular nowadays, and these are called description logics, often abbreviated as DLs eventually. In fact, description logics are a family of languages, and we will see a simple one and then maybe another slightly not so simple one. Now, just to recap, when we looked at FOL, the problems that we encountered were that it is computationally expensive. That by and large finding proofs is a computationally expensive proposition, and in fact proofs themselves can be quite long essentially. And the reason for that is that we assume that we have a flat structure in which there are all kinds of statements, and then a chaining process essentially has to find all the related sentences and link them together. So, that if you want to show that something entails something, then you have to find a whole sequence essentially. So, not only is it computationally expensive, it is in fact undecidable, or as we said, it is semi decidable in the sense that you can always build systems which will terminate if there is a proof, but if there is no proof, which means if the formula that you are talking about is not a valid formula, then it could go on forever essentially, and there is no way of knowing whether it would this thing. So, from this we move to the idea of frames, and the whole point of frames was to keep related info together. And connected, so that inference engine does not have to go searching for facts which are related and so on and so forth. They are all connected to each other and in some sense directly accessible. But the problem was frames was that no logical basis. That it depended entirely on the user to define the frame structure, and whether what was being represented was correct or consistent was totally left to the user to decide essentially. So, today we will look at description logics, which are a subset of FOL, and in general we are interested in decidable subsets. Sometimes we would look at subsets which are computationally inexpensive. So, as I said, description logics are basically a family of languages. And like any family of languages, there is a trade off between what you can express and complexity. As expressivity increases, complexity also increases essentially. So, you can have languages in which you can say more and more, but then to make the inferences that you want to make, the complexity can be higher and higher essentially. Now, if you remember when we were talking about semantics of first order logics, we had said that if there was some domain D, then we could define a set of abstractions. So, below this line is concrete things and above the line are abstract concepts. So, below the line is the real world or the domain, and some thing called concepts, categories you could define. So, for example, we said that there is a subset of the domain which is called man, and there is another subset of the domain which we will call mortal, and this would map to an concept in the set of concepts. Likewise, this would map to a set of concepts essentially. So, in some sense, when you talk about concepts, every element of that set is a concept, and when you talk about the domain, every element of this set is a individual essentially. So, domain contains individuals, and we can have another set of concepts essentially. Then of course, we talked about aggregation hierarchy. That things come together to make larger things. So, for example, a car is made up of 4 wheels and an engine and a chassis and a brake system and a petrol tank and all this kind of stuff. So, that is the aggregation hierarchy we talked about, and then there was also the abstraction hierarchy. Now, description logics, they focus only on this set, by and large only on this set. They have also been called as terminological logics or terminological systems. Or languages, or some people call it taxonomic logics, because essentially they focus on the concept of concepts and the relation between concepts, and the main relation between concepts that we are interested in at this moment is this taxonomic relation, which is basically the abstraction hierarchy, in which you say that for example, tigers are mammals and mammals are animals and this kind of stuff essentially. So, one thing which is different in description logics from FOL is that they do not have variables. Or quantifiers. So, if you were stating, if you wanted to say that the set of men is a subset of the set of mortal creatures, or in other words all men are mortal. In FOL you would have said for all x, man x implies mortal x. Whereas in DL, as I said, there are no variables, there are no quantifiers, you can only talk about concepts. So, language only allows you to talk about concepts essentially. You would simply say that man is a subset of mortal. It is a language in which we do not use quantifiers over the domain at all. So, remember that the quantifiers in first order logic were over the domain D. We could say things like for all x, or there exists an x, and so on and so forth. Description logic is not talking about the domain, though it does talk about individuals in the domain, because eventually we want to talk about some specific elements, and we will see how it does that, but it does not allow you to make statements about individuals like first order logic does. The only statement it allows you to make about an individual is that the individual belongs to a particular class essentially. So, we can say for example, that Clyde is an elephant, you are allowed to say about that much essentially, but the rest of the language is focused on talking about concepts or categories and making statements like elephants are mammals and mammals are animals and white elephants are elephants and other kinds of classes. So, essentially these languages are languages for describing sets essentially. In some at the basic level you can think of these languages as allowing you to talk about sets essentially. So, it is not just things like animals and mammals and so on, you can say the class of all those people who have two daughters who are both doctors. No, you can make statements like this, and but you cannot talk about that in terms of that for all x, if x is a person and there exists a y such that y is a daughter of x, and there exists a z such that z is a daughter of x, and x is and y is a doctor and z is a doctor, you do not say all that kind of stuff. So, there is no x, y, z involved, there are no variables involved, you can only talk about concepts essentially. So, in fact, there are three kinds of things you can talk about in description logics. You can talk about concepts, and we will use the terms C, D and so on to stand for concepts. You can talk about roles, and roles are essentially binary relations. For example, friend, father, mother or any such binary relation, and we will use the term typically R and S to stand for rules. And the third thing is individuals. For which we will use letters like A, B and so on essentially. So, these three things they form what we call as a non logical or domain specific part. And this particular description logic that we will start by looking at, which is the language given in Brackman and Levesque, uses this logical set of alphabets. So, the logical part of the language consists of punctuation. So, just like we defined first order logic by first defining an alphabet and then defining terms and then defining formulas and so on, we are also now defining the this particular description logic essentially. So, you have punctuation symbols, then you have positive integers 1, 2, 3 and so on. Then you have what they call as concept forming operators, and these are particular to this particular language. Okay. So, I should say, I should qualify this as in Brackman and Levesque. Later on maybe we will use a look at some alternate notation which is more common nowadays, but there is no fundamental difference between that notation and this notation, it is just a matter of syntax essentially. So, these operators are all so, there are just 4 operators and these are concept forming operators. So, what is the basic idea is that you want to be able to describe concepts in terms of other concepts. So, people also say that DL is a logic of noun phrases. So, you can define concepts and you can define more concepts in terms of the given concepts and so on and so forth. So, you can say for example, a surgeon is a doctor who has specialized in surgery. So, you are describing surgeon in terms of doctor and the fact that people who have specialized in surgery essentially. So, a computer science graduate is a student who has got a degree and whose subject was computer science. So, all these separate descriptions so to speak come together to describe concepts, and the language that we are looking at, or at least we will start by looking at, is a language which allows you to describe concepts in terms of these 4 operators, which is all, exists, fills and essentially. And then finally, the logical connectives, because we want to be able to talk about sentences. And there are 3 of them. So, one is this arrow sign, one is this sign and the third is this sign. We will shortly see how these things are used. So, just like we did for FOL, we can talk about interpretations. DL. So, we can define a domain D and a mapping I to define an interpretation. So, for a concept C, the interpretation of C is a subset of a domain. So, I should not use this symbol, I should just use the mathematical subset symbol essentially. So, just as unary predicates we defined in first order logic, man, mammal, dog, cat and so on, which were subsets of the domain. A concept in description logic is also a subset of a domain essentially. For a role R, the interpretation of a role is a subset of D cross D. So, roles are essentially binary relations essentially. So, you can say John is a friend of Mary and that kind of stuff essentially. Then for an individual, A, the interpretation of A is an element of the domain D essentially. Exactly like constants in first order logic, they are just elements in the domain D essentially. So, let me talk about the use of connectives first and then we will move to concept forming operators. So, the connectives or the sentences of DL are of exactly three kinds. You can say that a concept C is this. We read it as saying that C is subsumed by D. That is one kind of a sentence. So, by what do we mean by a sentence of a language? The sentence of a language is something which can be true or false essentially. Right. So, there are only three kinds of sentences in description logics. One is that a concept is a sub concept or is subsumed by another concept D, and the semantics of this, as you can imagine, is that the interpretation of this must be a subset of the interpretation of this. Then we can say that C is the same concept or is equivalent to the concept of D. And as you can imagine, the semantics of that is that the two sets must be the same. What are these sets? These are the interpretations. Remember we are talking about a domain and then a mapping essentially. So, every concept is mapped to a unary predicate, so to speak, in terms of D. And then we can say that A belongs to C is equivalent to saying that A is a C or is a member of C. And you can imagine that the meaning of this is that the interpretation of A must belong to the interpretation of C. So, essentially all description logics, not just the one that we are discussing right now, all description logics, they talk about concepts, roles which are binary relations between concepts and individuals which belong to concepts, and that is about it essentially. And the only kind of statements you can make is that a concept is subsumed by another concept, or a concept is equivalent to another concept, or a concept or an individual belongs to a concept essentially. But of course, the real interesting part comes because you are able to define concepts in terms of other concepts, and the advantage that we get by this definition which we are about to see is that the kind of questions we want to answer, which is basically the truth value of these three kinds of sentences that we have seen, that are, for example, tigers mammals essentially, or are people with 3 daughters humans or something like that essentially. So, any such kind of concepts which say that one concept is a sub concept of another concept can be answered efficiently, as opposed to in FOL those things could become undecidable or exponentially long and things like that. So, all these description languages that we are going to see are motivated by answering these questions, that is a concept a sub concept of another concept, or our 2 concepts are equal, which is basically amounts to saying that both are sub concepts of each other, just like the subset relationship. And what class does an individual belong to essentially. So, what can you tell me about John, for example? So, I can tell you John is a surgeon and he is a graduate and that kind of stuff. So, all that information, which is a concept, all surgeons who are graduates and so on and so forth, we can answer essentially. The complexity of answering this question depends on the language that we are using, and we will see that this particular language, which is described in Brackman and Levesque, is a nice language in the sense that complexity is always linear in the size of the formula. It only depends on how big that formula is essentially. It does not depend upon the size of the knowledge base, which is different from what was happening in FOL. In FOL, the number of formulas you had would essentially decide your complexity, because you had to look at all the formulas to see if there is something matching or not essentially. Here that is not the case essentially. So, let us look at concept forming operators. So, we look at them one by one. The first operator we said was all, and the way to define a concept is all R D, where R is a role and D is a concept. It can be a arbitrarily complex concept essentially. This particular language that we are looking at only allows you to define concepts in terms of other concepts, but there are richer languages which allow you to define roles in terms of other roles. We will not look at that immediately, but maybe if we have a spare class we might look at that essentially. So, you can say, for example, the parent role is a super role compared to the father role. So, father is a type of parent, mother is a type of parent, whereas this particular simpler language that we are looking at does not allow you to talk about roles in terms of other roles, but concepts only in terms of other concepts essentially. So, what is this concept we are defining? So, let me first illustrate it pictorially. So, supposing this is your domain D, and there is a concept in this D which is given by, let us say, these So, this is what? This is the image of D. It could be anything. Let us say doctors, T stands for doctor or something like that. So, all the people who are doctors form this concept called doctors essentially. Now, we are saying that this is a set of. So, I am using the term set, but more often we might say a class. This is a class or something. So, set of all individuals whose role fillers are from the class D. R is the role. So, if let us say R is equal to child and let us say D is equal to doctor, then all. So, we will use a colon before a role name. So, all child, and we will use uppercase as in the book for this thing, is a set of all people. I am just using the term people, but all individuals is more correct, whose all children are doctors. So, all R D essentially saying this, essentially it is defining a new set essentially. So, let us say that there is somebody here in this blue circle that you can see, who has 2 children, let us say, which you can use this H for the role. So, the arrow points to a child. So, here is this person whose 2 children are doctors. Here is another person whose one child is a doctor and one child is not a doctor, it is something else. And then here is a person who has only one child who is a doctor, and let us say this person has no doctors, and some people do not have children also. So, we must take that into account, and here is a person who has no child who is a doctor. So, given this knowledge base, where essentially the red dot stands for doctor and the blue dot stand for other people essentially, which is a set that we are talking about here. We are talking about the set of all those people whose all children are doctors. So, this must belong to the set, this must belong to the set, and there is no other person whose all children are doctors, but there are people who do not have children. So, they must also belong to the set. Remember that universal quantification, that if you do not have a child, then you can say all your children are doctors essentially. So, everything which is in the square bracket is this set here. So, formally you can write it that the interpretation of this is a set of all those x's which belong to D, such that if y belongs to D and the image of x and the image of y belongs to this relation R, then the image of y must belong to the set D. So, that is just the formal semantics of the concept of all R D essentially. So, it is a set of all those, see it is only in the semantics we are using this variable x essentially. The language simply says all R D, and what does all R D talking about? It is talking about a set of individuals who are defined by the fact that all their children are doctors essentially, all their children must be doctors essentially. Okay. So, let us look at the next one, which is exists n R, where n is a positive integer. So, again let me start with semantics. So, if there is a domain D and there is a role R, let us say child or something like that, and the knowledge base has these kind of things. So, let us say this arrows point to children and so on. So, there is some role which is defined and there is a domain D essentially. What does this stand for? This stands for all individuals who are related at least to n individuals by R. The role or the relation is R essentially. So, if I say for example, exists two child, then it is a set of all those people who have at least 2 children. So, we look at the roles that we have. So, we see that this is a person who has 3 children. So, he should or she should be part of this set, this person should be part of the set, this should be part of the set, this should be part of the set, and this should be part of the set. So, those 5 individuals are part of this set essentially. I can remember that when we give the definition, then these definitions are generic in nature. You can nest them. You can say for example, all child exists to child, because this is a concept and all R is related to a concept essentially. So, what does this concept say? How would you read this?
Every child has at least every child has 2 childs.
Yeah. So, all those people, so I will use the term people whose all children have at least 2 children. So, these two concepts that we have looked at, all and exists, can be combined. In fact, any concept can be combined. Wherever we use the term concept, we can put in a compound concept essentially. Let us look at the next one, which is fills role C. I should say A. If I am using A for so, this is simple. If I have this domain D and there is this individual called A, this is basically the set of all those people who are related to A. If there are other people who are related to somebody else, it does not matter, but this set, and they could also be related to somebody else, that is not a disqualification. As long as they are related to A, we are interested in those people essentially. How would you define the semantics? It is a set of all those people X such that there exists a Y such that Y sorry interpretation of y is equal to a and x comma so, as an example you can say Phil's voted Alvin essentially. So, this is a set of all those people who voted for Alvin essentially, where Alvin has to be a constant essentially, right. And lastly, we have and d1, d2, dn. And let me just write the interpretation of it directly. So, this and is basically like a English language and you are saying that the person must be a d1, the person must be a d2, the person must be a dn, if you are talking about people here. So, basically the intersection of all the images of these things. So, these are the 4 concept forming operators that this particular language allows essentially. So, in the next class we will move towards. So, we will first look at an example or maybe another example in the next class. Then we will see what is the process by which we can make answer some of the questions that we were interested in essentially.